In this video, we're going to look at families of solutions and initial value problems. So let's start with a warm-up. We're going to find the derivatives, or we're going to integrate. Depends on what it's asking us to do. On A here, x is our dependent, and in fact, I could write this as x of t if it makes it easier for you to think of this as e to the t plus 5, where my dependent is x of t. Either way, I'm going to do x prime of t, or just x prime is totally fine. This is just going to be e to the t. B is a little bit easier because it's more familiar than what we're used to. So f prime of t is going to be equal to the cosine of t. If I were to integrate on c, we know this is going to integrate into e to the t plus 5t plus c. Nice, easy integration. And on D, if we were to integrate this, this would give us negative cosine of t plus c. Now we know from what we just did that when x prime is equal to x, this happens when my x, or f of t, is equal to e to the t all day long. And if we put on this multiplier of c, e to the t, where the multiplier c is a parameter, that this also will work. We know that the derivative of e to the t is e to the t, and the derivative of c e to the t is c e to the t, for all c that are real numbers and they're the parameters. This means we found an infinite set of solutions for a first-order differential equation that satisfies x prime is equal to x. When that happens, these are called one-parameter family of solutions. A family of solutions. We know from calculus that when we find the antiderivatives, we are finding a family of antiderivatives at work by adding on that plus c. Because we know the derivative of e to the t plus 5t plus 7 is the same derivative as e to the t plus 5t plus 10. So we know that from our calculus that these are a family of antiderivatives. Therefore, when we have x prime is equal to x, when we're looking at our differential equations, these are called one-parameter family of solutions. And each member of the solution set is determined by figuring out what the constant's going to be. Now, if we were to plot the different c values, and when I'm talking about the different c values, I'm not talking about the plus c. In particular, I'm looking at x of t is equal to c e to the t. This one in particular is what I'm looking at. That when c is equal to 1, then this is what it'd look like. If c is equal to 2, this is what it'd look like. If c equals 0.5 or 1/2, this is what it'd look like. A -1, a -2. And of course, when c is equal to 0, we get 0, and that is not exciting. I mean, it's not even interesting. When we talk about the n-parameter family of solutions, basically we're just integrating our c e to the t, or e to the t, an infinite number of times, an n number of times, if you will. Then what's happening is that the only thing that's changing each time I integrate it is I'm going to have some arbitrary constant that keeps adding on. And as a result, we expect all of those n-order differential equations to have the same n-parameter family of solutions. When the family of solutions contains every possible solution, then we call it the general solution. So we're going to talk about that more when we ask for the general solution. And it's much less cumbersome than to say the n-parameter family of solutions, to just call it the general solution. There are some one-parameter family of curves that are not quite general solutions because it does not contain a function that satisfies all the differential equations. For as an example. So let's take a look at this example. We have the first derivative is equal to the function squared. I know the notation's a little weird still. First derivative is equal to the function squared. We look at a particular function, x sub 1 of t, is equal to 1 over c minus t. It's going to be a solution of this differential equation. But this particular function, x sub 1, is undefined when t is equal to c. And we know when that happens, it's not going to equal to 0. This thing is also never going to equal 0. This function is never going to equal 0. Now, if I take a second function, not a family, not from the same family as x sub 1, but a second function, total stranger, x sub 2 of t is equal to 0. This is also a solution of this differential equation. So we know that we can get some solutions, but those solutions in this example are not family members. They're total strangers. If I'm asked to find the differential equation for the family of x is equal to c t cubed plus 1, then the first thing I'm going to do is I'm going to differentiate my equation. When I do that, I get x prime is equal to 3c t squared. Now, if I solve for c, c is going to be equal to x prime over 3t squared. If I substitute this back into my original equation, I have x is equal to x prime over 3t squared multiplied by t cubed plus 1. And I simplify this, I am going to get x is equal to x prime over 3 multiplied by t plus 1. Now, if I were to multiply everything by 3, I would get 3x is equal to x prime of t plus 1. And what we typically like to do is we like to have x prime equals 2, but you don't necessarily have to do that. We could bring everything to one side of the equation, and so we get x prime of t minus 3x plus 1 is equal to 0. And this is a differential equation for this family of functions. Find a differential equation for this family. Well, we're going to do something similar. We're going to go ahead and do the derivative. So x prime is equal to c. Well, x prime is equal to c. Well, okay. Let's put that back in for c. So x is equal to x prime multiplied by t plus x prime quantity squared, and I wrote c, x prime, x prime, the quantity squared. Bring everything to one side of the equal sign, and I'm typically going to start with the highest power. So I'm going to have x prime squared plus x prime t minus x is equal to 0. And here is a differential equation for the family of functions described as x is equal to c of t plus c squared. Now, if I want to find a particular family member, then I need to have a point in which I need that family member to go through. And we call that an initial condition. So a first order differential equation with one initial condition or one initial point that I want my family member to go through is called the initial value problem, usually abbreviated as IVP. And the solution of an IVP will always be called a particular solution of the differential equation. If conditions are given at two different values, then we call this a boundary value problem. And this is much harder to solve. We're not going to do that in this video. It will usually be the case that if an algebraic formula is given for a general solution of an nth order differential equation, then it will contain n constraints, and n initial conditions will be required to find that particular solution. A linear differential equation, which has the form of x raised to the n th. This should be x raised to the nth, like that. Should be in the form of ax plus b. In general, what we know is that the coefficient on my x's and even any of my x to the nth power, as well as my x of t, depends only on the independent variable t. And that's it. And doesn't depend on the variable x and its derivative. So another way you might see this is a sub n t x raised to the n of t plus a sub n minus 1 t x to the n minus 1 of t plus dot, 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 dot. And eventually we're going to get down to the very last term, which is a sub naught, and then t, and then x of t, there's no derivative on that, which is equal to my function, we'll call it f of t. So this is a linear ordinary differential equation. And the reason I know it's linear is the way I look at it is that t itself doesn't have x of t in the denominator. There's no quotients with x of t in it. There's no products with x of t in it or in its derivatives. And that's how you can tell whether or not this is a linear function. Let's take a look at our first example here. Find all the solutions to the differential equation x prime of t is equal to negative t sine t. So we know that x prime of t is equal to negative t sine of t. So what I'm trying to do is I'm trying to find x of t. So I'm going to integrate negative t, the sine of t, dt, and this will give me my original function. And as we know from calculus 2, this is integration by parts, where u is equal to t and du is equal to dt, and dv is equal to negative sine of t dt. That means v is equal to the cosine of t. So when we get done doing this integration, I'm just going to cut to the chase. This is going to be negative t cosine of t minus the sine of t, and then don't forget the plus c, and this is going to give me the x of t. So that is nothing new. We have done integration before. It's just the way that it's presented is slightly different. Now I have an initial value. And this is similar to when we solved initial values in calculus 1 or 2. We know that x double prime of t is equal to t to the fourth. That means x single prime, the first derivative, must be this integration of t to the fourth dt. Well, we integrate this and we get t to the fifth divided by 5 plus c. So now we have x prime of t, that's a terrible x. Try to save it, it didn't work. So x of t is equal to t to the fifth over 5 plus c. Now, we have this initial value right here. We're going to use this initial value. So we know that x prime of 1 is equal to 1 to the fifth divided by 5 plus c. This has to equal negative 1. So we get our first c. C is going to be equal to negative 1 minus 1/5, so that is going to be negative 6/5. So x prime of t is going to be t to the fifth divided by 5 minus 6/5. Now, we still haven't found my original function, but we know that x of t is going to be the integration of t to the fifth divided by 5 minus 6/5. dt. So when we integrate this, we're going to get t to the 6th divided by 30 minus 6/5 t plus c. Notice I always try to put a tail on my t because my pluses and t's kind of look alike. All right, going back up here, we have the other initial value that we're going to use to find this c. Remember, we are looking for a particular family. Any family member in here will satisfy this derivative, but we want a particular family member. We're chasing a particular family member, and so we're going to use this second one, which is x of 1, which is 1 to the 6th divided by 30, minus 6/5 multiplied by 1 plus c has to equal 2. And when I get done with this, I'm going to get c is equal to 19 over 6. So the family member that I am chasing, my final answer is x of t is equal to t to the 6th divided by 30 minus 6/5 t plus 19 over 6. And what we just did on these two examples is not anything really different than what we did in Calculus 1 and 2 when we were looking for a particular family member when we integrated and we had an initial value. Nothing new there. We want to show, in this next example, we want to show that each member of the one parameter family of the functions x is equal to ce to the 5t is a solution to the differential equation x prime minus 5x is equal to 0. Now remember, I'm just reminding you, I know because this is still new, these x's are functions of t, just a quick little reminder. So what we're going to do is we're going to go ahead and take the derivative of x of t, which we know x of t is ce to the 5t. So that's nothing new. That means x prime of t, or just x prime, is going to be 5ce to the 5t. If we substitute this into the equation right here, we're going to get 5ce to the 5t, that's my replacement for x prime, minus 5, my replacement for x was ce to the 5t, and we can say this does indeed equal 0. Therefore, each member of the one parameter family of functions that satisfies x is equal to ce to the 5t is a solution of this particular differential equation. Now, we want to find a particular family member. So if we want to find the particular family member, in other words, I'm trying to figure out what the c is, then the way I'm going to do that is I'm going to use the initial value. Now, this is different. I'm not going to have to integrate. I know the output is 2. So I know x of 0 is equal to ce raised to the 5 multiplied by 0, which also equals 2. So ce to the 0 is equal to 2. Well, e to 0 is 1, so c is equal to 2. So the family member that I am chasing, x of t, is 2e to the 5t. This is a particular family member that I want for the general solution. So here, this is a family of functions that satisfies this differential equations. Here's a particular family member that will also satisfy this differential equation. Okay, now we're going to show that each family member of the two parameter family of functions, where x is equal to c sub 1 sine of 3t plus c sub 2 cosine 3t, is a solution of the differential equation x double prime of t and plus 9x is equal to 0. And then I'm going to find a particular solution. So if I have a two-parameter family of functions, bam, I need two initial values. So I need two initial values. And I have one that looks like it's not, but there is actually two here. And I don't know what happened to the prime. There should be a x prime of pi over 2, which is equal to x of pi over 2, which is equal to 1. and I want to make sure that that satisfies my two-parameter family of functions, satisfies that differential equation, and then I'm going to find a particular family member. So the first thing I'm going to do is take the derivative of my original function. So I'm just going to rewrite my original function, c sub 1, the sine of 3t, plus c sub 2, the cosine of 3t. So x prime of t is equal to 3c sub 1, the cosine of 3t, minus 3c sub 2, the sine of 3t. It's just doing the derivative. Nice, easy derivative. Now I'd like to say, hey, can I put this in and see if this is a solution? And the answer is no, because it wants the second derivative. The differential equation is a second derivative plus 9 times the original function is equal to 0. So I'm going to have to go one more step, and I have to find the second derivative of t, which is 9c sub 1. Oh, it's a negative 9c sub 1, the sine of 3t, minus 9c sub 2, the cosine of 3t. So here's my second derivative. Now I'm going to see if I take my second derivative, which is negative 9c sub 1, the sine of 3t, minus negative 9c sub 2, the cosine of 3t. This is all my second derivative, plus 9 times my original function, which is c sub 1, the sine of 3t, plus c sub 2, the cosine of 3t, is equal to 0. And you can see that, yes, this does indeed equal 0. So I don't even have to question it. It does indeed. So I checked. This is a solution to this differential equation right here. Now, I want to find a particular family member. So to find a particular family member, I have to have two initial values. My first initial value I'm going to use is that the original function, when I put in pi over 2, is equal to 1. So x of pi over 2 is equal to c sub 1, the sine of pi over 2. 3 pi over 2. I was just so excited to put a value in. I dropped my 3. It's 3 pi over 2. 3 pi over 2, because I have this 3 right here. So don't forget that. And then plus c sub 2, the cosine of 3 pi over 2. And this equals 1. Now we know the cosine of 3 pi over 2 goes to 0. We know that the sine of 3 pi over 2 is negative 1. So I have negative 1, c sub 1 is equal to 1. That means c sub 1 must equal negative 1. So we found our first part of our family member. That's my c sub 1. This is why I need two initial values, is because I need to find c sub 2. So I'm going to come over here and I'm going to say, okay, my second initial value is x prime of pi over 2 also equals 1. So x prime of pi over 2 is equal to, so I'm going to put that into my second derivative. So 3 times my c sub 1 happens to be 1, the cosine of 3 pi over 2, and then minus 3 c sub 2, the sine of 3 pi over 2, and this also equals 1. Well, as before, this will go to 0. So I have negative 3 c sub 2. The sine of 3 pi over 2 is negative 1, is equal to 1. That tells me that c sub 2 is equal to 1/3. So the family member that I am looking for is going to be x sub t is equal to negative 1, the sine of 3t, plus 1/3 the cosine of 3t. So this is a particular family member that satisfies this differential equation right here, satisfies this differential equation, and satisfies this initial value. So something to note, and I, of course, wrote right over it, so let me erase that, is that the sine of AT and the cosine of AT have the property that their second derivative is equal to the negative of the original function, provided, of course, the coefficient on t happens to be 1. Just a little side note you might want to put in your notes. And that's it for this video.